Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Simply Supported Composite Beams, and it is going to provide you a broad overview of the composite beams and also the resistance to sagging bending. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the simply supported composite beams, then move on to the analysis of cross-section, then wrap up with conclusions. Composite beams in buildings are usually supported by joints to steel or composite columns. The cheapest joints have little fractural strength, so it is convenient to design the beams as simply supported. In this video, we will discuss the simply supported composite beams. The cross-sectional area of steel sheeting that is needed for the construction phase often provides more than enough bottom reinforcement for the composite slab. It is then usual to design the slabs as simply supported. The concrete is of course continuous over the supporting beams, and the sheets may be as well. These simply supported slabs require top longitudinal reinforcement at their supports to control the width of cracks. The width of slab considered in calculations B is usually taken as 1 meter, but for clarity, only a width of 1 wavelength is shown in this figure, except where the sheeting is usually deep. The neutral axis for bending lies in the concrete where there is full shear connection, but in regions with partial shear connection, there is usually a second neutral axis within the steel section. Local buckling of compressed sheeting then has to be considered. This is done by using effective width for flat regions of sheeting. The presence of profiled steel sheeting in a slab is normally ignored when the slab is considered as part of the top flange of a composite beam. Longitudinal shear in the slab causes shear strain in its plane, with the result that vertical cross-sections through the composite T-beam don't remain plane when it is loaded. At a cross-section, the mean longitudinal bending stress through the thickness of the slab varies across the width of the flange, as sketched in this figure. Simple bending theory can still give the correct value of the maximum stress at point D if the true flange width B is replaced by an effective width B or B effective, such that the area GHJK equals the area ACDEF. Research based on elastic theory has shown that the ratio B over B depends in a complex way on the ratio of B to the span L, the type of loading, the boundary conditions at the supports, and other variables. At a cross-section of maximum bending moment, the compressive force in the slab is usually independent of the effective width, being governed by the tension in the steel member. The width assumed has little influence on the plastic moment of resistance, so simplified values are used in both Eurocodes 2 and 4. For the mid-span region of a simply supported beam in building, it gives the effective width as LE over 8 on each side of the steel web, where LE is the distance between points of zero bending moment. The width of steel flange occupied by shear connectors, BO, can be added, so that B equal to LE over 4 plus BO, provided that a width of slab LE over 8 is present on each side of the shear connectors. Because of local buckling, the ability of a steel flange or web to resist compression depends on its slenderness, represented by its width over thickness ratio, C over T. In design to the current Eurocode, each flange or web in compression is placed in one of 4 classes. The highest, least slender class is Class 1, plastic. The class of a cross-section of a composite beam is the lower of the classes of its web and compression flange, excluding a flange restrained by concrete, and this class determines the design procedures that are available. This well-established system is summarized in this table. The Eurocodes allow several methods of plastic global analysis of which rigid plastic analysis is the simplest. The class of a steel web is strongly influenced by the proportion of its clear depth, d, that is in compression, as shown in this figure. For the class 1, 2, and 2, 3 boundaries, plastic stress blocks are used, and the limiting d over t ratios are given in the current Eurocode as functions of alpha, defined in this figure. For the class 3, 4 boundary, elastic stress distributions are used, defined by the ratio psi. Now we will discuss the beams with cross-sections in class 1 or 2. The main assumptions include the tensile strength of concrete is neglected. Plane cross-sections of the structural steel and the reinforced concrete parts of a composite section each remain plane. For plastic analysis of sections, the effective area of the structural steel member is stressed to its design yield strength Fyd in tension or compression. The effective area of concrete in compression resists a stress of 0.85 times FCD constant over the whole depth between the plastic neutral axis and the most compressed fiber of the concrete. The effective section is shown in Figure A. As for composite slabs, there are 3 common situations. The first 2 occur only where full shear connection is provided. They are explained assuming a simply supported beam. The first one is neutral axis within the concrete or composite slab. The stress blocks are shown in Figure B. The depth xc assumed to give the position of the plastic neutral axis is found by resolving longitudinally as this equation. This method is valid when xc less than or equal to hc. For the transverse sheeting shown, hc is the net depth of the concrete slab, where the slab is supported by secondary beams, and the sheeting runs parallel to the main beam. The gross depth can be used for that beam, because the loss of cross-section caused by the top rib is negligible. Taking moments about the line of action of the force in the slab, we have this equation, where hg defines the position of the center of area of the steel section, which need not be symmetrical about its major y axis. If the previous NCF equation gives xc larger than hc, then it is replaced by this equation. This force is now less than the yield force for the steel section, denoted by this equation. So the plastic neutral axis is at depth xc larger than ht, and is at first assumed to lie within the steel top flange, as shown in Figure C. The condition for this is this expression. The distance xc is most easily calculated by assuming that the strength of the steel in compression is 2 times Fyd, so that the force NAPL and its line of action can be left unchanged. Resolving longitudinally to determine xc, we obtain this equation. Taking moments about the line of action of the force in the slab, we obtain this expression. If xc is found to exceed ht plus tf, the plastic neutral axis lies within the steel web, and MPLRD can be found by a similar method. The third one is partial shear connection. Let us suppose that the shear connection is designed to resist the force NC smaller than NCF. If each connector has the same resistance to shear, and the number in each shear span is n, then the degree of shear connection is defined by this equation, where NF is the number of connectors required for full shear connection. The depth of the compressive stress block in the slab, xc, is given by this equation, and is always less than hc. The distribution of longitudinal strength in the cross-section is intermediate between the 2 distributions shown for stress in Figure C, and is shown in Figure D, in which C indicates compressive strength. The neutral axis in the slab is at a depth xn slightly greater than xc, as shown. There is a second neutral axis within the steel eye section. If it lies within the steel top flange, the stress blocks, as shown in Figure C, except that the concrete block for the force NCF is replaced by a shallower one for force NC. Resolving longitudinally, we have this equation. The depth of the neutral axis in the steel is found from this expression. Taking moments about the line of action of NC, we obtain this MRD equation. If the second neutral axis lies within the steel web, the stress blocks as shown in this figure E, and MRD can be found by a method similar to that for this MRD equation. A composite beam is usually designed first for ultimate limit state. Its behavior in service must then be checked. For a simply supported beam, the most critical serviceability limit state is usually excessive deflection, which can govern the design where unprobed construction is used. Now we will introduce the elastic analysis of composite sections in sagging bending. It is assumed first that full shear connection is provided, so that the effect of slip can be neglected. All other assumptions, as for the elastic analysis of reinforced concrete sections by the method of transformed sections, the algebra is different because the flexural rigidity of the steel section alone is much greater than that of reinforcing bars. In general, the steel section is assumed to be asymmetrical with cross-sectional area AA, second moment of area IA, and the center of area distance ZG below the top surface of the concrete slab, which is of uniform overall thickness HT and the effective width B effective. The effective slab thickness HC is the net thickness for transverse sheeting and the gross thickness for parallel sheeting, where there is no small top rib, as in this figure. These thicknesses are the same. The symbol N is used for whatever modular ratio is appropriate, so it is defined by this equation, where EC effective is the relevant effective modulus for the concrete. The symbol N is also used for number of shear connectors. It is usual to neglect reinforcement in compression, concrete in tension, and also concrete between the ribs of profiled sheeting, even when the sheeting spans longitudinally. The condition for the neutral axis depth x to be less than hc is this expression. The neutral axis depth is then given by the usual first moment of area equation. The second moment of area in steel units is given by this equation. If the condition is not satisfied, then the neutral axis depth exceeds hc, as in this figure, and is given by this equation. The second moment of area is this equation. In global analysis, it is sometimes convenient to use values of I based on the uncracked composite section. In sagging bending, the difference between the cracked and uncracked values of I is usually small. Stresses due to a sagging bending moment M are normally calculated in concrete only at level 1 in this figure, and in steel at levels 3 and 4. These stresses are shown here, with tensile stress positive. Deflections are calculated by the well-known formulae from elastic theory, using Young's modulus for structural steel. For example, the deflection of a simply supported composite beam of span L due to distributed load Q per unit length is this equation, where the shear connection is partial, eta less than 1. The increase in deflection due to longitudinal slip depends on the method of construction. The total deflection delta was given approximately as this equation, where k equal to 0.5 for probed construction and k equal to 0.3 for unprobed construction, where delta A and delta C are respectively the deflection for whole load acting on the steel beam alone, and on the composite beam with full shear connection. This expression is obviously correct for full shear connection, eta equal to 1, and gives a slightly low result when eta equal to 0. From conclusions, what we learned: many buildings are constructed with a steel framework composed of steel beams and steel columns, but mostly with a concrete floor slab. A much stiffer and stronger structure can be achieved by ensuring that the steel beams and concrete slabs act together as composite and so effectively monolithic units. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.